Okay, thank you. Okay, so sorry. Let's go ahead. All right, this one is going to be a little bit different. I'm not going to do a lot of notation on this one. I will give you the slides at about 6 o'clock tonight. I just want to make sure they're correct. So I looked at midterm 2023, midterm 2024. They had a set of problems: jet and plate, jet non-moving vane, pump power, sprinklers for 2024, jet reversal, and dimensional analysis for that one. And then I'm going to try and do a topic summary. When you go one of the things that as you go through all of these exams, try to figure out what we're asking. You may have other midterms that I don't have available. Okay, just as a sort of mention, I did these on my own. I don't know for sure that they are correct. I hope they are, and I think they cover everything, but there may be errors, and if you identify them, please tell me. Okay. Okay, so I have two large tanks. They contain water. One tank is emptying out. The other one is in static equilibrium. So the fluid is just stuck there. And we've placed a plate right here. And that plate is being impacted by a jet from the tank on the left. Obtain an expression for H required to hold the plate in place. Flow is uniform, frictionless, plate has negligible weight, blah, 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 blah. Okay, so uniform, well, there's things I should talk about. With a lot of these flows, especially flows out of tanks, you're going to use Bernoulli equation. When you use Bernoulli equation, you're making an assumption about the flow coming out, and you assume it's frictionless. We're going to draw CVs. I haven't drawn a CV on this one, but we got fluid coming out, and it impacts against the plate, and my CV is basically going to be the fluid coming out. You've done enough tank problems that you know that the velocity out of the left tank is going to be square root 2gh. I'll go through a more detailed solution. You have linear momentum, which is where you're going to have a force, which is m dot v. Hydrostatic force is stuff you did in chapter 2. And how do you get H to correspond to cap H? So jet velocity coming out is just going to be H. And if you do Bernoulli equation, you're going to have Gz equals 1/2 v squared. And GH, there you go. And so 2GH at the exit. So 0.2, 0.1, 1, 2 equals v squared, and you end up with v equals square root of 2gh. The mass flow rate out of the jet is just going to be rho times a times v. You're given the diameter usually in these problems. And the force exerted on the plate, the momentum equation, is just going to be m dot v, 2 rho agh. Any questions so far? This one's not a bad problem. Hydrostatic force is the force that's acting on the plate. And that force, oops, nope. Okay. That force is just going to be rho GHA. The force balance is the force of the jet against the hydrostatic force. And so if you balance the two of them out, you get rho on both sides. You've got G on both sides. You've got little h, big H, and A's. So the only difference between the two is H equals cap H divided by 2. So the height of this is just going to be half of the height. So just for fun and games, there. Oh, that's it. These are not meant to be overly demanding. They are testing you on concepts. So that's question 1. All right, so we got question 2. Question 2 tends to be this particular type of question where you have moving carts. And if you look back at the discussion that we had in lecture 19, I did a couple examples looking at moving carts. It's very similar. Okay, but here you're asked to find an expression for mass m to keep the cart stationary. Stationary nozzle produces a jet of liquid that strikes a vane on a frictionless cart. The vane turns the jet through an angle theta. So angle theta is here, velocity, and all you have is fluid going around it. So if you look back at the lecture 19 example on this moving cart, it's going to be very similar. For the second part, you're given a bunch of terms, and you're asked to find what the mass would be. The only difference here is that you're given a velocity of the cart. So steady flow, incompressible liquid, thin, smooth vane, speed unchanged relative to the vane. Jet fills the area at the vane. Cart moves to the right at V cart. There's a control volume, which is going to be fixed to the cart and vane, so you're just following along. And m dot equals rho times area of the jet times W. And W, in these cases, is referring to a relative velocity because the cart is moving. So Vj minus V cart. Now, when it comes in and you're defining the directions, make sure, unlike me, that you put an X and a Y. So W in, it's just Wi, the incoming fluid. W out is W cos theta I sine theta j. So velocity of the cart plus W, put everything together, and you get velocity in and velocity out. Any questions so far?
When you define the y and x in the way you did, would the velocity of the cart not be the positive one, or you just subtract it? Never mind.
You're just, okay, so really, again, as much as possible, do try to sort of do a couple relative velocity problems just to get yourself comfortable with them. I did a lot more detail when I looked at lecture 19. Again, sort of pushing back a little bit on some of the stuff I did do. But if you're, and this is a great time to sort of say, if you have a chance, you can look at the Mythbusters. And there's a really good video on YouTube where they take a cannon and put it on the back of a truck, and they drive the truck at 60 miles an hour, and they shoot the ball off the cannon at 60 miles an hour in the reverse sense, and it just drops down. And this is really helpful to visualize relative velocity. Not now, though. So if you have the linear momentum, once you know what the out and the in velocities are, there you go. You put the terms in. So visualizing these things is really hard. You tend to sort of counterthink yourself. You keep trying to figure out different ways to do it. The force on the vane is opposite to the force on the fluid. So you have force X, which is rho AJ W squared 1 minus cos theta. W again, Vj minus V cart. And you end up with the mass by sort of substituting all your terms out, moving everything around, has to be equal to mgfx. So you take all of your forces, divide it by g, and it reduces to that when, or sorry, it reduces to this if the cart is 0. This is going to be a very fast lecture because I'm giving you all the numbers. So I'm not going to, and I can't write these fast enough to keep up with all of this. So stationary cart, there you go, V cart equals 0. Put in the numbers anyways. And the V cart, or Vj minus V cart, so 15 meters per second minus 4, 11 meters per second, 45 degrees, 0.9 or 0.3 for the numbers. Substitute everything in, and you end up with 157.2 kilos. Again, as much as possible, don't look at these solutions before doing them. Check on them afterwards. It's perfectly fine to do that, and then make sure they're right. There you go. So if you want to check what's going on, and I can do that because I'm not writing an exam, I have theta equals 0 degrees, no deflection, there's no thrust, m equals 0. Theta equals 180, it's twice, and so you end up with twice rho ag w squared divided by g, and w greater than 0. And so the lateral reaction is just going to be rho ag omega, or w squared sine theta. Towards minus y, it does not affect m. Any other questions on that? Or any questions on this? These are all easy, right? Yeah. Everything, every time you do one of these exams, there's a tendency to look at the old ones and say the new one is harder. Here's another one where you're given a flow rate, diameters, so you have D1, which is 6 inches. You have D2, which is 4 inches. You have oil, which is flowing in there, and you have a mercury manometer. And you're given that the height of the mercury between the beginning and the end is going to be 20.4. In between the two, you have a pump. So you have gallons and horsepower. Find the pump power and horsepower. So from the figure, h equals 1.7 feet, delta z equals 0. Manometer equation, you have rho hg minus rho oil, which is times gh. Putting all the numbers in, getting all the things out, you get 24.56 slugs per cubic foot in terms of density difference. Calculating delta P, you get 1344.4 pounds force per square foot. And you kind of work in feet and English units.
If on an exam you were to give us in English units, would you expect us on our H sheet to have the conversions, or would you give them to us?
So for, I probably would not give you something like G, so 32.2 feet per second squared. If it were something a little bit more esoteric, so for example, horsepower, I probably would give you something that would give you guidance on that. But probably not for feet to inches. And you should know feet to inches. It's 12 inches to the foot, please. Continuing. Since you're dealing with a pump in the system, its adding head and you're given the pressure head, you're given the velocity head difference, and you can calculate the total pump head. And again, this is one of the reasons why I keep telling you, please look at the aid sheet, because on the aid sheet, we've got the extended Bernoulli equation and all of the rest. You are expected to be able to use whatever's on the aid sheet, and I will not, they won't be provided on the exam, of course. So familiarize yourself with that at the very least. Sorry. Okay. So 26 feet. So if you're given feet, it's rho g q, volume flow rate, times 26.03, and it's 1624 foot-pound 4 seconds. And you're given in the problem the 550 conversion, and so you need 3 horsepower to solve for that. Any questions on this one? This is going to be a fast lecture today. We're done with the problem 1 or exam 1. The second one, so this is last year's midterm 2, and I'm working with the same sort of problem sets, but please remember this is not, there's always differences between who's teaching the course and how they sort of emphasize different things. But generally, you can kind of expect some guidance from this. Simplified water sprinkler rotates in the horizontal plane. Water enters vertically and discharges horizontally from each jet. So it's coming out like that. Q equals 0.015 cubic meters per minute. Jet diameter is 5 millimeters. Radius of the sprinkler is 225 millimeters. And the pivot is frictionless. So we don't have to worry about that. And you have to find the torque to prevent rotation and steady state angular speed. So here we have a rotating system. So I'll grab one of the arms and look at that. The moment arm is the R, which is the lever arm. Mass flow rate is Q over 2 per jet, because we're going to assume that each jet is going to expel the same amount of liquid. Absolute velocity creates torque, and at steady state, absolute tangential velocity is going to be 0, and I'll explain that in more detail. And relative velocity is omega r. So the torque to prevent rotation, if you have Q is equal to 2.5 times 10 to the minus 4th, area, which is given, you calculate that directly. Velocity of the jet divided by 2, 6.366 meters per second. And the holding torque is just going to equal the torque from the jets. Rho Q V jet is the force times the moment arm, which is R. So if you put all the terms together, you end up with a torque of 0.358 Newton meters. The relative velocity is going to be Q times the number of jets over area and radius. And so if you put that together, you end up with 28.3 rads per second. And I still want to sort of hold off on some things. Okay. So probably one of the questions is, why is the absolute tangential velocity 0? Steady state means constant angular speed. So angular acceleration is 0. Since net torque is equal to I alpha, the net torque of the sprinkler must be 0. Right? There's nothing else there. Pivot is frictionless, so the only torque is the reactive torque from the jet. This torque must also be 0, and the torque from the jet is caused by the change in the fluid's angular momentum, which is proportional to the absolute tangential velocity of the exiting fluid. Therefore, for torque, velocity tangential must be 0. which means that the only velocity that we worry about is the relative velocity. So the relative velocity of the fluid leaving is omega r. This was a fun one. I did hear stories about this last year. Okay, so you were given water exits the nozzle, strikes a curved plate that reverses the flow. The force to hold the plate is 100 newtons. And that force is over here. Diameter 1 is 8 centimeters. Diameter 2 is 2 centimeters. The holding force, 100 newtons. There we go, 100 newtons. Velocities, you're asked to find velocities v1, v2. Those are easy because you have a manometer, you got a height, or no, you don't have the manometer height. You have manometer reading, which is h. So in this particular problem, you're actually going to backtrack all the way. You're going to extract out what the velocity is of the jet from the force. So that means it's a linear momentum problem. So there's two outlets. And if you haven't looked at this problem yet, this is a question I'll get in office hours at some point, and I'll probably get over the next few days, is how did they calculate the area at the exits? And what was the area at the exits? The two outlets are in the CV. So again, if we look at sort of defining everything, yeah. We have fluid coming back here, fluid coming back here, fluid coming in. If we let alpha be the mass fraction of the top sheet, then mx out times v out has to be alpha m times minus vr, 1 minus alpha m dot minus vr. And the vertical components cancel by symmetry. There's nothing that's going up and down. They're both equal and opposite. So they don't contribute to Fx. But you have this expression right here for velocity r. And if you add them all together, so you don't worry about the volume or the cross-sectional area at the exit at the top or the bottom, you end up with minus m dot vr. The force on the fluid is m dot vx out minus vx in, or the force of the plate on the fluid is less than 0. So force of holding on the plate equals negative force of the plate on the fluid. And so you could say m dot vx in minus vx out is m dot v2 plus vr. If this is what's happening, Vx in is plus V2, Vx out is minus Vr. And if you add, and that's how you get the plus sign. In order for this to be correct and to have the same amount of material entering and exiting, Vr has to equal V2. So if Vr equals V2, force is equal to 2 m dot V2, and you get up an expression that's 2 rho A2 V2 squared. If you had a deflection, just 2 seconds. If we had a deflection, you'd have forces m dot v2 times 1 plus cr cos theta, and cr equals 1. Setting cr equal to 1, theta equal to 0, you end up with the same expression at the beginning. Question?
Sorry, what was VR?
VR is the reversing flow. So VR, V1, so 1 minus alpha, alpha, VR. Tuck. I'm almost through this. Okay, so from Bernoulli, if I know the velocity coming out, Bernoulli from 1, nozzle exit, Bernoulli from 1, P2 is approximately 0 at the free jet, and reading is rho hg minus rho wgh. I think maybe I mixed up my note. Oh no, P2 is correct. P2 is 0, That's the exit. So you add all the terms up. P2 is 0 in the open atmosphere portion, and you end up with V2, which is equal to 12.62 coming out of the jet. V1, which is in the pipe before the area constriction, ends up being 0.789 meters per second. Oops. So you have had to reverse what you would normally do. Normally we'd tell you here's the measurement at 1 and 2. You'd get the velocity at 2, and then you'd say, hey, this works out really well. But here you're going to do the exact opposite. You come back. Your P1 is equal to 1/2 rho V2 squared minus V1 squared. And you can calculate that with all of the information you did in the previous part, and you get 79,000 pascals, or 79 kilopascals. P1, then divide by rho to Hg, mercury minus water divided by Ng, and you get 0.644 meters. So mercury, water, difference in density, and the difference with respect to water is, or mercury to water is minuscule. Any questions on this one? Go ahead.
For this exam, if it's not given, do we assume the density of water is 1,000 kilograms per meters cubed or 997?
We'll give you a number. We'll give you a number, or we will give you some advice. If there's, that may end up being something I have to check. But. And so the last one from this particular exam was one looking at dimensional analysis. And again, you've got droplet size d from a jet depends on nozzle diameter, jet velocity, fluid density, fluid viscosity, and surface tension. And you're asked to write this in dimensional form. And one of the things that when you do dimensional form problems on exam, we often give you some help. So d rho u are the repeating variables. So you don't have to go through this to sort of figure out what's going on. Now, on all of these terms, you have an aid sheet. That aid sheet has all of these units on it. If you don't look at it before the exam, you will not be able to find them. I can almost guarantee it. But if you do beforehand, you'll know exactly where everything is. You reduce all of the terms, list the variables, list the dimensions. You've got the repeating variables. You've got the pi groups. You'll end up with pi 1, which is geometric similarity. And even if you don't know what to do with surface tension and free droplets, you should get Weber number directly out of this. In fact, you should expect to get the first two just by inspection. Don't do it by inspection. Do it by the pi theorem. But you should be confident that you're going to get a Reynolds number because it's got velocity and you've got diameter, and so there you go. Weber number you may not expect, but it's on that chart. So droplet terms, length, velocity, length over time, density, length, or mass over length cubed, viscosity, mass over length time, and surface tension, mass t squared. You're not expected to know these. You should kind of, well, the first four you know, you should know. And again, these are things that you should know sort of because we've done it enough. Total variable 6, fundamental dimensions 3, pi groups 3, and d rho u. You can calculate all the terms, and I haven't done the complete job here. It's really, it's a little bit of algebra, but you end up with pi 1, which is d over d, pi 2, which is Reynolds number, and pi 3, which is going to be Weber number. Go ahead.
Question. So I know like in the examples you solve, you usually take wave density and velocity as the repeated variables. But what happens if you take surface tension?
Well, first of all, on this exam, you were told to do that.
Yeah.
Okay. If you do, then try it. Try and see what happens. You'll have a bit of problem because you won't end up with the d over d term. Right? So you'll end up with a length scale that depends on surface tension. It's not going to make much sense. But generally, again, you're looking at it, and if you look at the last lecture where I did an example on cantilevered beams, yeah, deflection, thank you. You can see what happens when there's a repeated index or a repeated unit on two terms. Okay. These are not meant, or this list is not meant to be comprehensive, but it sort of gives you an idea of where everything is coming from in previous exams. So linear momentum, relative velocity, manometry, extended Bernoulli, unit conversion. Unit conversions always, you really should be able to do unit calculations. And if you're dealing with a dimensional problem, you should always have that. In terms of angular, or 2024, angular momentum, linear momentum, Bernoulli and manometry, dimensional analysis. Everything changes year by year, but you can see where the scope of this is. Velocity concepts, everything really, just as a reminder, absolute versus relative velocities. You have plenty of opportunities to look these up. Extended Bernoulli equation, we didn't do, or we did talk about it, lecture, it would probably be lecture 21. Manometer analysis, you did that with Professor Gunther. Dimensional analysis, Buckingham pi, and physical meaning of Reynolds, Weber, Froude numbers. Again, as much as possible, if you look at that 8 sheet, I've given you that sort of information there. You should be very comfortable with continuity and momentum equations. So there's continuity and momentum equations. You should also be very comfortable with drawing control surfaces, outward normals, how pressure acts, and control volumes. And you ended up, maybe just sort of highlight, on both of those are the integral forms, but generally you're not dealing with the integral forms, you've got the steady state flows. And the steady state flows are the equations that are just below. M dot 1, or M dot out minus M dot in, all of that together to get the terms. Same thing with angular momentum. I have sort of kind of looked at the exam just to sort of get a sense. Sorry, I've looked at these two exams to get a sense of what might have been some issues. Relative velocity, sign conventions, particularly in momentum equations. Momentum equations often turn out to be very challenging. So spend a bit of time convincing yourself that you're comfortable with it. Units, just as a piece of advice, 9.81 feet per second squared is not gravitational acceleration. Manometers, calculating sine, or avoiding sine arrows. Always draw your CV. I didn't do it in this. I did do it when I was doing the examples in class for the lecture. Always include your units. Your units are probably the best thing that you have to sort of check and see whether something makes sense, particularly when you're dealing with dimensional analysis. Check limits. Do the extremes make sense? And any assumptions, list them out. All right, standard, that's all standard. So in terms of important equations continuity, linear and angular momentum, and the extended Bernoullis, where you add in the effect of pump or any other type of term that you add into the flow. Try to at least be familiar with Reynolds number. Mach number is not so hard to sort of follow through with. Froude, Weber, and Euler. Froude is more comfortable for your civil engineering colleagues. Weber is more something that your chemical engineers do. Euler, yeah, I guess Euler is one we do with aerodynamics. So there you go. So tying this all back to the book, it's chapter 2, 3, 4 in both texts. There's chapter 1 in the sense that there's units and all of that, but the emphasis is really on relatively, or chapter 5 too. Chapter 2, 3, 4, and 5, but chapters 3, 4, and 5, or sorry, not 4. Oh, not 4. Oh, that's a mistake. It's 5, or 3. Chapters, no, not 4. Ew. See? You get sleepy and you forget. Yeah, chapter 3, chapter 3. We have nothing on chapter 4. Okay, just so it's clear. Phew, okay. Chapter 5, similarity and dimensions. That's what we've been focused on for the last week. And that's a good place for me to stop unless there are questions. I'm happy to stick around for 14 minutes. Oh, and one other thing. This will be posted at 6 o'clock. And if I forget, ignore chapter 4 stuff.
I feel bad asking these. If these failed gravity,
Sorry, I can't see it. Can I?
yeah. Shows over there.
Oh, yeah, that's gravity. Oh, that's, oh. Okay, sorry. I have to look at what that is, but that's an acceleration term. It's total acceleration, not G.
I couldn't figure out what that was.
Yeah, that's a mistake. Okay.
This is really helpful, thank you. Also, I have a question. When you're doing dimensional, I came across a dimensional problem, and it was from another exam.
Hold on, I'm just going to